Hi, everybody. This is Dr. Nigro with a screencast. I'm going to post it to Physics Fundamentals, but this was a problem that came up in one of my physics classes this week, and I wanted to make sure everybody understood how this problem was completed. All right, so we've got Grace, who is leaning out of a window, and she's going to throw a ball straight up into the air. And as the ball comes back down, Grace misses the catch and it lands on the ground. The ball was in the air for a total of 3.5 seconds. All right, so for this problem, just to keep things simple, I'm going to use a gravitational value of negative 10 meters per second squared. And as I tell my students, in physics, one of the easiest things to do and the most helpful, in my opinion, is to start with a picture of that motion. All right, so here's Grace. Now she's not on the ground, she's in a window, and she's going to throw a ball up in the air and miss the catch, and it's going to pass her and then impact on the ground somewhere below her. So there she is. Okay. Now, the first part of our problem, if Grace threw the ball with an initial velocity of 12.5 meters, how long did it take the ball to reach its maximum height? All right, so on my picture, I'm going to be looking at what happens from her initial throw to the star, the maximum height. And so with that information, I have some knowledge about my different variables, my initial velocity, final velocity, acceleration, time, and change in position. All right, the problem gives me the initial velocity of 12.5 meters per second, and I know that gravity is always a constant, and since we're using negative 10, we'll list that there. All right, now I know the time, but the time is for the entire throw, so that's not going to be particularly useful here, and that's what the question asks us to find anyway. So here's our unknown, which means I must either know the displacement or the final velocity. So if I look at maximum height, I know that the velocity should be 0 at that point. So the V final is going to be 0 here. All right, so with this information, I can use my acceleration formula, which is final velocity minus initial velocity divided by time, plug in my values, so negative 10 meters per second squared for the acceleration, 0 minus my initial velocity of 12.5 meters per second, divide that all by my unknown time. All right, then I'm going to do some rearranging with algebra, and I find that it's going to take about 1.25 seconds for the ball to move from her hand to its maximum height. Okay? All right, so let's look down at our next one. This one wants to know what is that maximum height. So again, we're going to be at the star in my picture. So let's list our variables again, just so we're clear. All right, we know that our initial velocity will be 12.5 meters per second. Our final will be 0 at this point. We're going to be using a gravitational constant of negative 10 meters per second squared, and we calculated our time would be 1.25 seconds. So our unknown this time is the change in position. All right, we have a lot of variables filled in, so we have a lot of choices. We've been working quite a bit with the final velocity squared equals initial velocity squared plus 2 times acceleration times that change in position. So I think I'm going to use that here. All right, so 0 for my final velocity, 12.5 meters per second for my initial, and then 2 times negative 10 meters per second squared times my unknown of change in position, delta y. All right, so I'm going to do my math. I'm going to move my 12.5 once it's squared to the other side, which will make it negative, and then I'll divide that by negative 20. So I'm going to end up with a positive answer, which is reasonable because the ball is moving upwards, and I get 7.81 meters here. All right, now this is not the only way you could have done this. I mean, you could have used the change in position is the initial velocity times time plus 1/2 at squared. That would have worked. Or you could have used our average velocity formula equals change of position over time. Just remember that if you use this formula, that average velocity is final velocity plus initial divided by 2, and then set that equal to the change of position divided by time. So either of those would have worked as well, and you still would have gotten 7.81. All right, so those two are pretty straightforward. All right. The next one's a little trickier, all right? What was the velocity of the ball just before it hits the ground? All right, so if we go back up to our picture, I'll change my pen color. All right, we want to know, well, what is the velocity value right here where I put the red star? All right, so the ball's going to start at the initial position and go up and down. So let's see what variables we have to work with here. All right, so if I start at the beginning of the throw, then my initial velocity will be 12.5 meters per second. All right, I'm looking for that final velocity, so that's be unknown. I'm going to use negative 10 meters per second squared for gravity time. Now, if I go back and look at the problem at the beginning, it tells me the ball is in the air for an entire 3.5 seconds. So I know the time from when she releases it till it impacts the ground. Right? I don't know that change in position, but if I look at what I do know, I have enough information to solve for V final. All right, so my final velocity will be equal to my initial velocity plus acceleration times time. All right, so I plug in 12.5 meters per second for my initial velocity, negative 10 meters per second squared for my acceleration times 3.5 seconds for my overall time. Plug that into my calculator and I get a value of negative 22.5 meters per second. All right, now remember the negative sign here is only telling us that it's moving downward, right? If I ask myself if that's reasonable, if I go back up to my picture, if I drew a line right across my motion, right, when the ball passes Grace, it should be moving at a velocity of negative 12.5 meters per second, all right, which means that as it continues to fall past Grace, it should continue to speed up. And our final velocity is greater than that velocity. So this is a reasonable answer, all right? Now, I'm going to slide down underneath. We'll come back to this last question because I want to talk about a second way that we can work that question to find that final velocity, all right? So we have initial velocity, final velocity, acceleration, time, and change in position. I'm just going to fill these back in. 12.5 meters per second. Our unknown is the final. All right, our acceleration is negative 10 meters per second squared, 3.5 seconds. All right, so that's if we look at that entire motion. I'm going to draw my picture again too. Okay, but we could instead have looked at the top of that motion where we have the star. All right, and if we do that, that's going to change a couple things for us. First, we're no longer having an initial velocity of 12.5. If we're at maximum height, that velocity value will be 0. All right. Similarly, the time won't be 3.5. All right. We know based on our first calculation that it took 1.25 seconds to reach that maximum height. So if I subtract that 1.25 seconds from that 3.5 seconds, that will give me the time it takes for it to fall from maximum height to the final position down at the bottom. All right, so now I have velocity, I have acceleration and time. So I'm going to use the same formula. Final velocity equals the initial velocity plus acceleration times time. We're going to plug in a 0 this time for the initial, negative 10 meters per second squared times 2.25 seconds. And we get, again, negative 22.5 meters per second. So you can see we got the exact same answer as when we worked it the other way. All right. So as I tell my students all the time, in physics in particular, there's not usually one way to get to the answer. Usually there are a couple different paths that you can choose. All right, so let's move on to the last question. Well, how far above the ground is the window? All right, so this time we're going to be looking for that change in position that is specific to the distance between when the ball was thrown and the ground. All right, so this is the delta y that we are interested in. All right, so let's list our variables: initial velocity, final velocity, acceleration time, change in position. Again, there are a couple different ways to do this. You can look at it in terms of the initial at the very beginning all the way to the end. So that's what I'm going to do first. So I start with 12.5 meters per second. My final velocity is negative 22.5 meters per second. My acceleration is negative 10 meters per second squared, and the whole time is 3.5 seconds. So you may ask, well, why can I do that? Well, this is displacement that we're solving for, not distance. And because of that, as the ball goes up and then comes back level with where she threw it, we've worked right back to where we started. And then the remainder will show up as our calculation here. All right, so let's try. All right, let's see. What do I want to do? Maybe this time I'll do the change in position is equal to initial velocity times time plus 1/2 AT squared. All right, you could use the V final squared equals V initial squared plus 2A delta X. That would work too. All right, but we did that up there, so let's try something different. All right, so we've got 12.5 meters per second times 3.5 seconds plus 1/2 -10 meters per second squared times 3.5 seconds squared. All right, so if we plug that into our calculator, change in position. All right, our 12.5 times 3.5, that's going to be 43.75 meters because our seconds will cancel. And then we're going to have 3.5 squared times 20, basically. Oh, no, times 5, sorry. And this is going to be, whoops, wait, I did something wrong. What did I do there? Oh, no, sorry, times 5. This is going to be a negative 61.25, whoops, meters. So she have a meter in there. Whoops, come on. All right, and we'll say minus 43.75. And so we find that the change in position is negative 17.5 meters. All right, now again, the negative sign is just telling us the direction, and that's accurate because the ball is lower than where it started, so we should have a negative value there. All right, now similar to the problem above, there is a second way to do this problem, which I'm going to do down below. All right, so we took the entire distance that time, so we could do something similar to what we did above, where we start at the top, all right? Or you could even come over and start right where it pulls even, where your V initial would be negative 12.5 meters per second. So you're either going to start with an initial velocity of 0 or negative 12.5 meters per second. All right, I think for this one, I'm going to start again at the top because I just think that that's a little conceptually easier to see. All right, so we've got our variables. We've got an initial velocity at 0 because we're going to start at max height, a final velocity of negative 22.5 meters per second, our acceleration due to gravity of negative 10 meters per second squared. And we saw above that we need to use not the full time, but 2.25 seconds. And then our unknown, which is the change in velocity. All right, so with this information, you know what? This time I will use the V final squared equals V initial squared plus 2 times the acceleration times change in position, just to change it up. All right, so negative 22.5 meters per second squared equals 0, because our initial velocity is 0, 2 times negative 10 meters per second squared, and then our unknown change in position. All right, so we plug things in. We're going to end up with 506.25 meters squared second squared equals negative 20 meters per second squared times our change in position. So we're going to divide 20 to the other side, and we're going to find that our change in position is again equal to negative 17.5 meters. So you can see again, there's a different way to get to the answer, but the answer is going to be the same. Okay, so one thing I talk about quite a bit in my class is the flexibility of problem solving and having a picture and really thinking about what's going on at different points within the motion of your object is very useful in finding alternative ways to solve problems. Okay? All right, let me know if you have any questions.